Hi friends, welcome to another video on control systems. In this video we'll see the transformation of circuits. We'll see interesting things about transfer function of circuits. So before I start, let us go through these initial slides. Okay, this is the obvious thing you should know before you uh, start this video. And of course, you have to spend some quality time with this video so that you get the best out of it. Okay, fine. So with this, we will start. Okay, this is what I have now. Uh, I want to, of course, in the previous videos, we have seen that the transfer function of this particular circuit diagram, which is V naught of S by V in of S, happens to be 1 over 1 plus S R1 C1. So this is what is the transfer function of this. Let me take another similar type of circuit, so with different values of R and C. So let me take this as R2, C2. Again, let me take it as this is V naught of S, and this is again V in of S. So naturally, V naught of S by V in of S of this particular transfer function is similar to this. Now, only thing is that the resistance and capacitances are different. Fine. Let me consider this is having a resistance of this is 100 ohm and this is zero point 0.1 microfarad, and let me consider this as 1 kilo ohm and this as 1 microfarad. Suppose if I say this is your first network and this is your second network. For the first network, suppose if I write the pole 0, the pole of this particular thing is at minus 1 over tau 1. So where tau 1 is this into this, so naturally this comes out to be as minus suppose if I do it, I think it is minus 10,000. So it is 100 into 0.1 exponential minus 6, sorry, minus 6, this is minus 6, and the 1 over that is okay, this is, it is just okay, 100 into 0.1 exponential minus 6. This is like okay, 100k. Is that 100k? And we have this P2 is, of course, if I say this is second circuit, which is minus 1 over tau 1, or if you say this is tau 2, where tau 2 is R2 C2, where tau 1 is R1 C1. So where is the pole of this? So pole of this is at minus 1000, correct? So this is the pole positions. If I write this is at minus 100k, whereas this will be at minus 1k, minus 1k. So this is the pole position in S plane. S plane when you take it individually. So what I do, I will now cascade these two, or you can write the block diagram representation. Can I write this as the block diagram of first circuit? This is a block diagram of second circuit, which happens to be 1 over 1 plus S R1 C1. This is 1 over 1 plus S R2 C2. So if I say this is V in of S and V naught 2 of S, so let me say this is V naught 1 of S. So what is V naught 2 of S? V naught 2 of S by V in of S is naturally the product of this, which happens to be 1 over 1 plus S R1 C1 into 1 plus S into R2 C2. This will end up with, the overall transfer function will end up with a pole at minus 1k and a pole at minus 100k. This is what is expected system. Suppose if you do cascade of these two systems in block diagram as. So what we'll do now, so we will electrically do it and see what is, so whether do we end up with two poles when I join these two. So what I'll do is I will just connect it. This is R1. I will connect, this is C1, this is now R2, and this is C2, this is V0 of 2. Let me say this as V1, this is Vn. So let us consider this as I1, this as current I2. Let us take all of them with respect to time. This is V of t small. So I want to find V0 of S, V02 of S by Vn of S, exactly the way how I found it. So let me replace, so we know, okay, how do we find the transfer function of this cascaded system. I will do that. So let me replace all capacitors and input voltage and currents by Laplace. So this is what I have. This is Vn of S, this is V1 of S, this is R1, this is R2, this is 1 over SC1, this is 1 over SC2, this is I1 of S, V0 of S, this is I2 of S. This is what the Laplace. Let me quickly write the signal flow graph. So what is I1 of S? I1 of S is V in of S minus V1 of S by R1. Again, what is V1 of S? It is nothing but I1 of S minus I2 of S. That's what is current flowing through this, multiplied by the impedance of C1, which is 1 over SC1. Again, what is I2 of S? I2 of S is given by V1 of S minus V0 of S by R2. Now what is V0 of S? It is I2 of S multiplied by 1 over SC. This is current multiplied by the impedance is the voltage. Now let us draw the SFG. So this is V in, this is I1, this is V1, this is I2, this is finally V2. So what is I1? It is V in of S by 1 over R1 and V1 of S minus 1 over R1. And this is V1 of S is I1 of S into 1 over SC1. This is minus 1 over SC1. And this is again now, of course, now by this time you know what is, how do I'm writing this. So this is minus 1 over R2, this is 1 over SC2. This is what the signal flow graph is. Signal flow graph. So V0 of S by V in of S is nothing but 1 over delta summation of I is equal to 1 to N P1 delta 1. So N is equal to 1 because you have only one forward path. So this equation becomes, this is actually Pi. So it will become P1 delta 1 by delta. So what is P1? The forward path is 1 over R1 into 1 over SC1 into 1 over R2 into 1 over SC2. So delta 1 is actually 1 minus 0. What are 1 minus of minus the product of gain products, loop gain is 1 over SR1C1. It is this. And how about this? You can take out this minus sign outside and I put it here, plus 1 over SR2C1 plus 1 over SR2C2 plus these two are non-touching. So it becomes 1 over S square C1 C2 R1 R2. So upon simplifying I can write, so what is this? This is V0 of S by V of S is equal to 1 over S square R1 R2 C1 C2 divided by, if you take LCM, this will become S square C1 C2 R1 R2 plus S into R2 C2 plus S into R1 C2 plus S into R1 C1 plus 1. So of course divided by S square R1 R2 C1 C2. So this will go with this will go with it. So we will ultimately end up with 1 over A square R1 R2 C1 C2 plus S into R2 C2 plus R1 C2 plus R1 C1 plus 1. Correct? This is your V naught of Qs by V of S. This is upon cascading these two individual blocks. So this and this we have cascaded, we end up with this as the transfer function. Let us find the pole position. So let me find the pole position. So what are the values of R and C you have? So let us substitute R1 is equal to 100 ohm, R2 is equal to 1 kilo ohm, C1 is equal to 0.1 microfarad, C2 is equal to 1 microfarad. So then this transfer function will become 1 over A square into, so it is 100 into 1 exponential 3, it is now 100k multiplied by 100k multiplied by 0.1 into 1 exponential minus 12. This happens to be 0.1 picofarad plus S into what is this? R2C2 is 1 milli. R2C2 is 1 milli because this is 1 kilo into 1 micron plus R1C2. R1C2 is 0.1 milli plus R1C1. It is 100 into 0.1 exponential minus 6 is 10 micro. 10 micro plus 1. So what is this now? So it is now 1 over what is 100 exponential 3 into 0.1 exponential minus 12. Can you see this is A square into 10 nano plus S into, it is 1 exponential minus 3 plus 0.1 exponential minus 3 plus 10 exponential minus 6. This happens to be this is it is actually 1 exponential minus 3 plus 0.1 exponential minus 3 plus 10 exponential minus 6. So it is 1.11 milli plus 1. So let us find the roots of this. So if I want to find the roots of this, it is now so let me find out this equation. Number of its degree is 2. It is 10 exponential of minus 9. Then this is 1.11 exponential of minus 3. Next it is 1. So roots are, so I can write it as 1 over S plus 908.33 is one root. How about the other root? Other root is at S plus, if I do the engineering, so can you see this is 110.091k, correct? Now what is interesting to see here is that what we thought was uh, see now, the point here is, this is the individual poles were there at minus 1000 and minus 100k, the individual poles. The moment you connect it, this is not, of course we expected, okay, this should be at minus 1000 and this should be at minus 100, minus 100,000, but they are not at that point, because when you cascade we were expecting this, but where actually we are getting the first pole. The first pole is at minus 908.3. The second pole is at minus 110.09 k. Now instead of having it at minus 100k, this was supposed to be at minus 100k, this has slightly moved away. This was supposed to be at minus 1k, but it is at minus 908. The point here, what we are trying to understand is, the moment you cascade these individual circuits, the overall transfer function is not simply the product of these two. Why it is not the product of these two is because this circuit will going to load this circuit. So because of loading effect, the poles are not at the intended position of their individual poles. This pole which was there supposed to be at minus 100k now has moved to minus 110.09k, and this pole which was supposed to be at minus 1000k, minus 1000, so now this is at minus 908. So this is purely due to the loading of second circuit on the first circuit. Suppose if I want to get, so of course if you can see these two blocks, this block is not actually loading this. So conceptually, since this is not loading this, you are having the equivalent transfer function having poles at minus 1000 and minus 100,000. So this is what you are having, but here it is totally different. Then how do we ensure that you get the poles at exactly at intended minus 1000 and minus 100,000? That is possible if this circuit doesn't load this circuit. So how to ensure that this doesn't load this circuit? So I will put a buffer in between these two, meaning, so I will write my circuit here. This is my first circuit, this is R1, this is R1 C1. Now before I connect it to next, I will put a buffer. This buffer has got a gain of 1. This buffer has got a gain of 1. What is more important thing is that this has got an infinite input impedance. This has got an infinite input impedance, and this output impedance is 0. So you have this. So this is R2 C2. What is this? This is a buffer. This is a buffer with unit, with gain is equal to unity, with gain equal to unity. Now how do we realize this? This is V in, this is V naught. Now if you are asked to find the write the what the variables, this is I1, this is V1, so this is V2, this is I2, and this is V1. So how do we realize this? So in practice we realize this using an op-amp as a voltage follower. You can see this how I can realize. You have this circuit, use a voltage follower here. This is plus, minus is there. You connect this. See here. This is my circuit. So this is R1, C1, R2, C2. The variables are, this is I1, this is V1, this is V2, this is V0, and this is I2. So now if you have this, so then how do I write the circuit now? How do I write the circuit? So what is for this circuit or this circuit, what is I1? I1 is nothing but V in minus V1 by R1. What is V1? It is this drop, that is uh, I1 multiplied by 1 over SC1. What is V2? V2 is actually gain of this multiplied by V1. So it's actually 1 into V1 is V2, because you have a gain of 1 by this voltage follower. So that's why it is so. Correct. So now what is I2? I2 is given by V2 minus V0 by R2. What is V0? It is I2 multiplied by 1 over SC2. Let us write the SFG for this. It is V in I1, V1, V2, I2, V0. Let us write this. So this is 1 over R1. This is minus 1 over R1. So this is actually 1 over SC1. This is 1, and I2 is 1 over R2. This is minus 1 over R2, and this is 1 over SC2. Now write the SC2. So write the gain. So which is nothing but V naught of S by V in of S is equal to, what are the forward paths? It is 1 over R1 into 1 over SC1 into 1 over R2 into 1 over SC2. Of course, into 1 is there. Into 1 is there. Divided by loops are these two loops. It is 1 plus, okay, let me take out negative sign of both the loops. 1 over S R1 C1 plus 1 over S R2 C2, and since these two are not touching, you will get one more term, which is 1 over S square R1 R2 C1 C2. Take the LCM and rearrange this. So this LCM will just take out this. This will become 1 over S square R1 R2 C1 C2 plus S into R1 C1 plus R2 C2 plus 1. This is V naught of S by V in of S, V in of S. So upon substituting the values, what we'll get here is, upon substituting uh, R1 as, what is the value of R1? So R1 as 100 ohm, R2 as 1 kilo ohm, C1 as 0.1 microfarad, C2 as 1 microfarad. If you substitute these values to this, this will become 1 over S square 100 into 1k. This what is 100 into 1k. What is this is now 0.1 micro into 1 micro plus S into, how much is R1? It is 100 into 0.1 micro plus 1k into 1 micro plus 1. So this happens to be 1 over, I think we already have it, S square, this is 10 nano plus, anyhow this is 1 milli, so it is 100 exponential 100 into 0.1 exponential of minus 6. Sorry, let me make this one. Okay, 100 into 0.1 exponential of minus 6 is 10 micro. It is S into 10 micro plus 1 milli plus 1. So then this is S square 10 nano plus, how much is this, 1 exponential minus 3 plus 10 exponential of minus 6 is actually 1.01 milli S plus 1. So what are the roots of this? The roots of this is now 1 over, so let me find the roots. 1, 2, this is 2 variables, and you have, sorry, this is done. sorry, 1. Okay, degree is 2. It is now 1 exponential of this is 10 nano. This is 10. Sorry, 10 exponential of minus 9 is a value, whereas b is 1.01 exponential of minus 3, and c is 1. If you solve for the roots, so 1 is s plus 1000, and what is that? So now I think I made a mistake there. So this is 1 plus, where is that? This is supposed to be at s plus 10,000. Correct? See now. So are we getting what is intended? See now. See the difference between this circuit and this circuit. So what is the major difference between these two circuits? Of course, this circuit is simply cascading. Here it is the same circuit, but in between this, before cascading, I am putting an amplifier with a gain of 1. It's like a buffer. It's like a buffer. When we actually put this, when we cascaded this, the poles were there at minus 908, and minus 110k, minus 110k. Whereas the individual poles are at minus 1000 and minus 100k. So this was the intended one, but when you connect it like this as it is, the poles were there at this point. But the moment you put a buffer, we know that when you put a buffer, the input impedance, since it is infinite, for this buffer, this circuit is not loading this, so because this circuit is not loaded by the subsequent circuit, so what is the resultant of this not loading? So it has now resulted in a pole at minus 1000, which is due to this, and the pole due to this is at minus 100k. So whatever you intended the poles to be at minus 1000 and minus 100,000, you are getting it because you have used a buffer. Circuit wise, this is having a gain of 1, but in terms of pole position, so they are totally different. So this is now at the expected position of minus 1000, this is there at the expected position of this. So now you can see this circuit will exactly resemble this block. This circuit will exactly resemble this block, because this block is not loading this. So that's what we usually say. So you can ensure that this doesn't load this if you have a buffer. If you have a buffer of gain. If you don't have a buffer, if you put it like this, suppose if this is the circuit as it is, so then this is going to load. So this way we can able to see the impact of loading on the pole position. The pole positions were supposed to be here and here. They were not there when you simply connected, but they were there at these two positions when you are putting a buffer in between the two circuits. So whenever we write the block diagrams like this, so whenever we cascade the thing, we always ensure that this block is not loading this, or any block is not loading the other block. So in circuit wise, if you want to realize that, you need to put a buffer. So this is actually loading. So in order to avoid the loading, you need to put a buffer of gain. So this is what is interesting about the loading and ensuring that it doesn't load the circuit. So that is possible only if you are adding a buffer in between the circuit. Thank you.